Good morning. In today's session, we are supposed to study about the linear predictive coding. So here, linear predictive coding is one of the most powerful speech analysis technique. If you see, we can use this method for the signal source modeling in the speech signal processing. It is often used as format extraction tool because it is giving us a signal source modeling. So it has wide application in other areas also. We can use LPC analysis that will be most appropriate for the modeling ovals, such as we can use as periodic. LPC is based on the source filter model of the speech signal, because if you see, we can use this method. It is the most useful tools for encoding, because it is giving us very good quality speech at a lower bit rate, and it will provide us extremely accurate estimates of the speech parameter, and it is relatively efficient for the computation. The most important aspect of the LPC is the linear predictive filter, which allow us the value of next sample to be determined by the linear combination of the previous samples. It means what? By using the linear predictive coding, what we can do here, we will get the higher quality voice. So it will provide the rate of 64 kilobits per second, and it will reduces this to 2400 bits per second. It means what? It is reducing the rate. At this reduced rate, the speech has distinctive synthetic sound, and there is a noticeable loss of quality. However, but that speech will get audible. It means what? It still can be easily understood. Yes, of course, we will lose here something, because here we are reducing the rate from 64 kilobytes to only 2400 bytes. It means what? Here we will get the noticeable loss quality, but here that audio is still also audible, and it can easily get understood. Since there is a information loss in the linear predictive coding, we can say it is the lossy form of a compression. So here we are saying LPC that will start with the assumption that speech signal is produced by a buzzer at the end of the tube, and here we are saying that will produces the buzz. So here, which we can characterize by intensity and frequency, and we will get that vocal tract forms the tube. It means what? Which is characterized by its resonance, and we are calling these as a formants. So here, when we are supposed to study about the LPC, this is nothing but the linear predictive coding. Firstly, we will go through the block diagram of this model. We will see what will be the concept of the LPC. So here, if you see, in the LPC we will have two frequency sources. These are nothing but one frequency source will get used to generate the unvoiced sound. Such sounds are generated when the speaker pronounces the letter, like you can take S, F, etc. It means what? Here we are supposed to take that unvoiced sounds, and another we are taking a noise source that can be used to generate such unvoiced sounds, such their frequency spectrum is wide, and here the voice sounds are simulated by the impulse generator, and the frequency of this generator we can vary depending on the our pitch of that sound. So this voiced as well as unvoiced. It means what? Here we can say we will require here two frequency sources for unvoiced sound and for the voiced sound. So here this voiced or the unvoiced frequency signal are we can pass through the filter. So this filter will represent the vocal tract which we will needed, and the input signal we can filter by this filter in such a way that we will get that letter that can be pronounced. So here we can say in the vocal tract, this operation we are doing with the help of tongue, lips, teeth. Thus, we can say when we are supposed to use LPC, at that time we can generate speech. Or we can say it is the model which is electrical equivalent to generate the sound. So here we can say LPC, when we are giving that format, LPC analyzer analyzes that speech signal by estimating the formats which we are now giving. We are saying this as a vocal tract which we are getting from our throat and mouth. So here when that signal will get estimated, at that time it will removing their effect from the speech signal and estimating the intensity and the frequency of remaining buzz. It means what? Here we are doing the filtering. So the process of removing the formats we can call as a inverse filtering, and the remaining signal we can call as a residue. So the numbers which describe the formats and the residue we can be stored or transmitted somewhere else. And LPC will synthesizes the speech signal by reversing the process. It will uses the residue to create the source signal, and it will use the formats to create a filter and run the source through the filter, resulting in a speech. So here we can say, because we will get the speech signal that will vary with the time, this process is done in the short chunk, which are called as frames. Usually it will require 30 to 50 frames per second, which will give us intelligible speech with a good compression. So here when we are supposed to do linear predictive coding, at that time we are doing the observation and output sequence. Observation of input and the output sequence that will produces the number of formats, and we will get the resulting set of coefficient which describe the behavior of system. It is used for predicting the sample. As the name given, linear predictive. It means what? It will predict that sample. And the set of that coefficient we can say as a all pole model, and the analysis then estimate the value of discrete time signal, because all these here we are using for a discrete communication, for a digital. So we can say the analysis then estimate the values of discrete time signal as a linear function of the previous sample, and the spectral envelope we can represent in a compressed form. So here we can say the advantage from the linear predictive is nothing but it will give a simplified vocal tract model. An analogy of a source filter model with the speech production system. So it is the useful method for encoding a speech at a low bit rate, because here we are supposed to reduce the bit rate. Here we will get the noise. That noise will get audible, but we will lose some information. That is the disadvantage. But we can say advantage, like it will give us audible sound, encoding speech at a low bit rate. So now we can see Lpc's block diagram. For that, you can see here Lpc will have main two components. These are nothing but it will require encoding, and another that will be the decoding, or we can say it will require two components. These are nothing but analysis or a synthesis. So the analysis part of the Lpc, linear predictive coding, it will involves examining the speech signal and breaking it down into a segment or the blocks. And here each segment is then examined further to find the answers to several key questions, like that segment is voiceable or unvoiced, what is the pitch of the segment, what parameters are needed to build a filter that models the vocal tract for the current segment. So here we can say when we are supposed to study about the block diagram of Lpc that will consist of two parts. These are nothing but encoding and the decoding. So we are saying here, when we are supposed to study about the encoding, that is nothing but the analysis. It will involve the examining of speech. So it will break that into some blocks, and each block is then examined further to find the answer, like what is the pitch of the segment, is the segment voiced or unvoiced, what parameters are needed to build the filter that model the vocal tract for the current segment. So here we can say Lpc encoder or a Lpc analysis is usually conducted by a sender who answers these questions and usually transmit these answers onto a receiver. Like we are saying pulse code modulation, delta modulation, all these are consist of the main three parts. Like this. Here also we are saying it will consist of three parts. These are nothing but the transmitter, channel and the receiver. Now we are talking about the transmitter. It means what? We are now talking about the encoder. So here we are saying it will break that speech signal into a segments, and here at the receiver it will perform the Lpc decoding, or we can say Lpc synthesis, by using the answers which we are received to build a filter that, when provided the correct input source, will be able to accurately reproduce that original signal. So initially, firstly we will see about the Lpc block diagram. You can see here we have drawn the Lpc diagram. So here we can see Lpc transmitter, Lpc channel and Lpc receiver. When we are talking about the Lpc transmitter, or we can say Lpc analysis, or we can say Lpc encoder, all are having the same name. What we are doing here? Here we are using Lpc transmitter will consist of analyzer, it will consist of coder, it will consist of pitch detector, or we can say it will have analyzer, it will have synthesis filter that will be at transmitter, as well as you can see that will present in the receiver also. And here when we are taking the voiced and unvoiced signal, and we are taking the signal from the synthesis filter, at that time we are supposed to give this to the multiplexer. So we can say here, when we are supposed to study about the Lpc block diagram, at that time you are supposed to write about Lpc transmitter and Lpc receiver. So in Lpc transmitter we can say here, if we are taking the signal, that is nothing but we are taking sampled signal, because here we are supposed to use discrete communication. So here we are taking speech signal, that is nothing but S of n. You can see here it is a digitized signal and it is obtained by sampling continuous time speech signal. So we can say it is the sequence of speech samples. It can be given to the Lpc analyzer. So analyzer will determine its coefficient for synthesis filter, because it is supposed to give that value to the coder. So we can say it will determine its coefficient, and after that, based on this coefficient, synthesis filter will reconstruct that speech signal, and reconstructed signal and the original signal, these are compared by the comparator, and here we will get the error. So the LP coefficient and the error signal we can get multiplexed by using the multiplexer, or we can say here we are using the coder. It is nothing but encoder. So here we will get the error signal, and the LP coefficient and the error signal will get multiplexed and transmitted. So we can say that signal as a Lpc signal. Now we are supposed to give that signal through a channel to the decoder, to the demultiplexer. So here excitation regarding voiced or the unvoiced input is given to a synthesis filter. So here now we are giving that signal, LPC signal, to the decoder. So now we can see about the decoder. Decoder will consist of, or we can say about the LPC synthesis. It will consist of demultiplexer or a decoder and the synthesis filter. LPC synthesizer, or you can say that is nothing but the LPC filter. So here the received LPC signal we are giving to the decoder or a demultiplexer, and it separates filter parameter and the error parameter, because you can see here we are using the synthesizer. So it will filter and it will give error signal that will get separated from the filter parameter, and the LP coefficient are given to the synthesis filter. Output of synthesis filter we can add to the error signal, which will give us original speech signal at the output. You can see here at the output also we are taking the same name, S out. It means what? Here again we are adding that error signal with the that synthesis output. So we will get the speech signal. Basically we are using here analyzer, that is nothing but the digital filter. So normally this parameter, this filter are updated every 10 to 25 microsecond. So for a reasonable speech quality we can take 10 to 12 parameters that can be used, and here it will get the bit rate of 3 to 8 kilobits per second. So now we can say about the human versus LPC production. You can see the diagram, block diagram for the human speech production, which is directly, and we can see about the voice which we will get by using the linear predictive coding. Voice coder speech production. You can see here the circuit, the block diagram for this. Here when we are talking about the human speech production, it will consist of our lungs, which will give us sound pressure. After that we will get some unvoiced excitation and you will get some voiced excitation. So we can say that is nothing but the vocal cords, and here that will give to the articulation. It means what? Our mouth and the nose, and you will get the speech. It is in the human speech production. Now we can see about the voice coder speech. It means what? When we are giving the excitation, at that time you will get the articulation. That is nothing but you will get the speech. How? Because when we are giving the energy, at that time your voiced or unvoiced decision, it will goes to the, we are using here two generator. One is noise generator and one is we are using for the voice or the unvoiced. It means what? We can say that as a tone generator. As we are saying, it will consist of mainly two generator. So we can say here it will goes to the tone generator and noise generator. So it will give the fragment that we can give to the variable filter, and after that we will get the speech at the output. So we can say according to the government standard 1014 we are using the LPC 10 because the input is sampled at the rate of 8000 sample per second, and this input signal is broken into a segment, and these we are giving to the encoder. After that we are giving that encoded transmitted signal to the decoder. It means what? To the receiver. So the 8000 samples in each second of speech are broken into a 180 sample segments, and this means that each segment represents the 22.5 milliseconds of the input speech signal. So we are using the LPC 10. So we can see here about the Lpc excitation. What we are saying here, before speech segment is determined as being voiced or the unvoiced, it is firstly passed through a low pass filter. with the bandwidth 1 kHz. It will determine if a segment is voiced or unvoiced. That is important because voiced sounds have a different waveform than unvoiced sound. So here the differences in between these two waveform, unvoiced and the voiced waveform, it will create a need for the use of two different input signal for the LPC filter that we are using in the analysis, that we are using in the we have seen we are using the synthesis filter in the receiver section. So we can say that will be in the synthesis, or we can say about the decoding. So here one input signal is for voice sound and other we are taking for the unvoiced sound. So the LPC encoder notifies the decoder if a signal segment is voiced or unvoiced by sending a single bit. There are two steps in the process of determining if a speech segment is voiced or unvoiced. The first step is to look at amplitude of the signal, also known as the energy in the segment. If the amplitude level are large, then the segment is classified as a voiced, and if they are small, then we can say that as considered as a unvoiced. And the determination requires a preconceived notation about the range of amplitude values, and energy level will be associated with the two types of sound. So here we can take voice speech segments that will have large amplitude, unvoiced speech segments which will have higher frequency, and that the average determining if a segment is voiced or unvoiced, we can get that information by the LPC decoder to accurately reproduce the speech signal. You can see here the spectrum of the voiced and the unvoiced, how it will look like. You can see the diagram. So here we are saying, in order to produce the input signal for the LPC filter at the decoder, it will need another attribute of the current speech segment, we can say as a pitch period. So the period for any wave including speech signal can be defined as the time required for one wave cycle to completely pass fixed position. So for a speech signal, the pitch period can be thought of as period of the vocal chord vibration, and that occurs during the production of speech. So we can say the pitch period is only we will needed at the decoding. Is not required for unvoiced segment. It will required only for the decoding of voice signal. So they are produced by the airflow, not vocal cord vibrations. So it is computationally intensive to determine the pitch period for a given segment of speech, because there are several different types of algorithm that we can use. But LPC 10 does not use an algorithm for the autocorrelation. Instead, it will uses the algorithm that can be called as an average magnitude difference function, which we can define as, you can see the formula. This we will not require, because here in our syllabus only we are supposed to study about the linear predictive coding. It means what? Only we are supposed to explain about this diagram, how we are doing in the transmitter for the voice and the unvoiced signal, how we are breaking that, and through the channel how we are giving to the decoder. So we can see here only for the understanding purpose, because LPC will be having the advantages because it is reducing the bit rate. That's why we are only supposed to see here. So we can say the advantages of the average magnitude difference function is that it can be used to determine if a sample is voiced or the unvoiced. And when we are applying that to unvoiced signal, the difference between minimum and average value is very small as compared to the voice signal. For unvoiced segment, the AMDF function, we also have a minimum when P equals the pitch period. So we can see now about the LPC articulation, then we will finish our unit. So we can see here we can use the LPC filter that is used by the, we can say as a LPC synthesizer, which we are using by the decoder to recreate the original input signal. So it is created based on the set of coefficients, and these coefficients we will get from the original signal during encoding when we are transmitted to the receiver for use in the decoding. So here each speech segment will have different filter coefficient or the parameters that it uses to recreate the original sound. Not only the parameters themselves different from the segment. So here we can say, but the number of parameters which will differ from the voice to unvoiced segment. So here if we are saying voice segment are uses the 10 parameter to filter, at that time we can say unvoiced will use only 4 parameter because there is no compulsion, both will have the same value. So a filter with n parameter is referred to as nth order filter. So in order to find the filter coefficient that will be the best match the current segment, being analyzed, the encoder attempt to minimize the mean square error. So we can calculate the mean square error as this given equation. So we can see here y of n is nothing but it is the set of speech samples for the current segment. A of I, it is the set of coefficient. In order to provide the most accurate coefficient, we can choose AI value that will be minimum, and AN, it is for all samples in the segment. So in order to solve for filter coefficient, we are supposed to estimate that error that is nothing but E of n. So we can see here, if we are having any uncompressed form, at that time, if speech is usually transmitted at 64 kilobits per second using 8 bit per sample and rate 8 kilohertz for the sampling, at that time LPC will reduces that rate to a 2.4 kilobits per second by breaking the speech into a segments, and we are sending that to the information to the decoder, and the pitch of that period we can quantize using the log compounded quantizer to 1 of 60 possible value. So here we can say by using the LPC coding we are supposed to reduce the bit rate, and here we are having different bit rate like 1 bit voice, unvoiced, 6 bit pitch period which will have 60 value, 10 bits K1, K2 which will each have 5 values. Like we will have lots of different 54-bit frame. So here we can say when we are supposed to do LPC decoding, it means what? LPC receiver. You can see here the block diagram. So here we are saying the process of decoding, it is nothing but here we are supposed to do decoding a sequence of speech signal which we will get from the encoding. So here we are supposed to do decoding of that sequence. That is nothing but here we are doing exactly vice versa, reverse process of the encoding process. Here each segment is get decoded individually and the sequence of reproduced sound segment is joined together, because in the encoding we were breaking that sound speech into a segment, but here now we are supposed to reproduce original signal. So here we are supposed to decode. So here we are doing the reproduction of that sound. So here we are supposed to join that together. Join together to represent the entire input speech signal, and the decoding, it is nothing but we are doing here synthesis of speech segment we will do based on the 54 bits, like we are saying we are having the different 54 bit frame. So here we are supposed to join this segment to get our reproduction of the original signal. So here speech signal is declared voice or the unvoiced based on the voice unvoiced determination bit, and here decoder needs to know what type of signal we are using. So what type of signal the segment will contain in order to determine what type of excitement signal we will given to the synthesizer filter, or we can say it will be the LPC filter. For voice segment, a pulse is used as the excitement signal, and this pulse will consist of 40 samples. So we can say for unvoiced signal, white noise is produced by the random number generator. So here we can see about the Lpc block diagram, which will have voiced and unvoiced noise signal. These we are giving, which we will get from the encoder. We are supposed to give that pitch to that voice unvoiced signal by using a switch. You can see here we are using here voiced and unvoiced switch. So by using switch we can give this to the LPC synthesizer, or you can say a LPC filter. So here we are rejoining these segments to get a reconstruction of signal at the LPC decoder. Here we have finished our first unit, in which we have seen about the pulse code modulations, which we are using to transmit analog signal into a digital. Here we have seen different types of modulations, like digital. We have seen about the pulse code modulations, delta modulations, differential pulse code modulations, adaptive delta modulation. Then we have seen the differences between these. So here we are saying, when we are supposed to do digital communication, at that time we are supposed to follow Nyquist rate, the sampling theorem, Shannon theorem, which will tell that we will require the frequency that will be greater than 2W. So we are saying here, when we are using the digital communication over the analog, it will have lots of advantages because it will give us data encryption. So only permitted receivers can allow to detect that data. Since we are using the digital communications, here we can use channel coding. So we can detect error and we can correct that error in the receiver. We will have digital communication with a wide dynamic range, and we can convert here data into a digital form. Here we can use multiplexing. That's why using multiplexing we will get speech and voice. Other data can be merged and transmitted over the common channel. And then what we are saying, if you see, digital communication is having some disadvantages, like digital communication will needed a synchronization in the case of synchronous modulations, and because of analog to digital conversion, because when we are supposed to use this type of modulations, we are taking signal that is nothing but analog. After that we are converting that. So because of analog to digital conversion, the data rate becomes high. Hence, more transmission bandwidth is required for digital communication as compared to the analog communications. And if you see, when we are supposed to study about the digital communication, it means what? Digital transmission of analog signal. At that time there will be numericals on the sampling theorem, signal to noise ratio. So you are supposed to understand about the sampling theorem, where we are saying a continuous time signal can be completely represented in its sample, and it will get recovered back if sampling frequency is the twice of highest frequency. So we are saying Fs will be greater than 2W, where we will get W is nothing but higher frequency. And what we are saying, we are supposed to use sampling theorem, which will tells that we will require sampling frequency will be greater. So Fs is nothing but it is the sampling frequency. So it will be required greater than 2W, means highest frequency. So here we have finished our first unit. Then we will see some numericals in the next session. Thank you.